Hello everyone. In continuation with our previous lecture, in this lecture we will discuss the remaining two methods to determine the particle size and particle size distribution. That is particle size determination by the sedimentation method and by Coulter counter method. So, start by the sedimentation method, particle size determination by sedimentation method. What is the meaning of sedimentation? Whenever there is a dispersion system, what is the dispersion system? Where the particles are the suspended or distributed in the system, they are not dissolved. If they will become dissolved, then what will happen? They become converted into the homogeneous system. A dispersion is the heterogeneous system, where the solute and solvent coexist. They exist together, but they have maintained their own identity. They will not dissolve with each other. So, in a case of a dispersion where the solute and solvent. So, as we know, just because of the presence of the gravitational force, which is directly proportional to the mass of the body, the particle will settle down, and the rate by which the particle will settle down, that is known as the rate of the sedimentation. So, the rate of sedimentation, by determining the rate of sedimentation, we can also determine the powder particle size, because the rate of sedimentation is also dependent on the particle size. The larger particle will settle rapidly as compared to the smaller particles. So, the instrument which is used for the determination of the powder particle size by the sedimentation method, that is known as the Anderson pipette, on the basis of the name of the scientist who has invented this, that is the Anderson. So, this is the picture or image of Anderson pipette. This is like simple pipette which you already you people are using in our laboratory. What is a pipette? Is the calibrated instrument by which you can calculate as a measure or transfer the 2 ml, 1 ml, 5 ml, 10 ml. There are different volume of the pipette is available. So, this is just like of the pipette and beaker, and the pipette and container arrangement, and the size of this container. In this container you can fill up to 500 to 550 ml liquid. सिंपल एक कंटेनर है जिसमें आप 500 से लेके 550 ml तक का लिक्विड यानी सस्पेंशन और डिस्पर्सन फिल कर सकते हैं. उससे अटैच देयर इज अ पिपेट, एंड द पिपेट एज अ टू 3-way कॉक. 3 डायरेक्शन कॉक मीन्स in the one direction when you move like this, then this opening will be here, and you can suck the 10 ml this volume from this container, and in this way you can withdraw the 10 ml sample in the sampling bin, and third way you can stop this, close this. So, this is the 3 direction cork, and this is the sampling bin, this is the pipetter, this is the suspension level, pipette and suspension. You have to fill the suspension in this container, and this is the height of that system. In this is almost a 500 ml suspension or sample you can fill in this. So, this is the arrangement of this different apparatus in this Anderson pipette. So, now how will you determine the particle size? Whatever the suspension or the particles you have for the determination of the particle size by the sedimentation method, you just remove of this pipette and fill that sample or fill that suspension in this container of this Anderson pipette. First we have to prepare 1 to 2% powder sample suspension. Either you have a sample powder prepared suspension, or if you do not have a prepared suspension, if you have to prepare a suspension by using this dry powder, you have to prepare 1 to 2% suspension. 1 to 2% suspension, that means the suspension should be very dilute. Why it should be dilute? Because if you want to determine the exact or accurate particle size distribution or particle size by the sedimentation method, then the sedimentation of the particle should be without any hurdle, without any disturbance. That means the flow of the particles should be uniform, streamlined, that is known as the laminar flow. And as we all know that for the laminar flow is applicable, this Reynolds number or laminar flow is applicable in the case of the dilute solutions or dilute suspensions only. So, for this we have to prepare the dilute suspension of the particles, for whom we are going to determine the particle size. So, first we prepare the 1 to 2% of the powder sample suspension. then deflocculating agent added in sufficient amount to break powder aggregate. So, there is a one stability issue with the suspension is that the flocculation, they may the particles they come closer and to make the flocks, and the rate of sedimentation of floccule will be more as compared to the individual particles. So, this will may lead to some error in the calculation. So, we have to prepare the very dilute suspension or dispersion of the powder by using deflocculating agent to, so that the flocculation process will be prevented. So, deflocculating agent added in sufficient amount to break powder aggregate. Sample filling, powder sample is introduced into vessel up to 550 ml mark. The vessel is shaking to distribute particle uniformly, just fill the powder particle, fill the liquid and shake the bottle, shake the container properly to get the uniform distribution of the particles in this vehicle. After that, the whole assembly is kept undisturbed in a constant temperature water bath. Undisturbed, because if you put undisturbed, if you kept it undisturbed, that there is a rate of sedimentation without any hindrance. If you will come and shake it in between, so what will happen? Their flow of the particles will not be streamlined. So, you have to kept it undisturbed in a constant temperature water bath, because the rate of sedimentation of the particles depends on the medium viscosity. And what is the viscosity of the medium? What is the medium here? The medium is the liquid, that is the vehicle. So, rate of sedimentation of the particle is also dependent on the viscosity of that vehicle, and this viscosity is temperature dependent. So, always keep this apparatus in the constant water bath, so that the viscosity, so to monitor to constant the viscosity of the solvent or the vehicle which we have used for the preparation of the suspension or dispersion. So, after keeping that apparatus in constant water bath, after filling the suspension or dispersion in this Anderson pipette, and keeping all the whole apparatus in a constant water bath, and then the next step, how will you proceed? At various time interval, 10 ml of samples, the pipette of that Anderson pipette is 10 ml capacity. So, at various time interval, 10 ml of sample withdrawn through a stopcock and poured it into a previously weighed china dish. The sample are evaporated and weighed accurately to correct and do the necessary correction is made to subtract the amount of the deflocculating agent which we have added during the preparation of that dispersion. Suppose that as you see in this picture, why we have in this diagram, it's a bigger particle and then a small particle, then a smaller particle. Why not all the particles are of same size? And all the particle will have same rate of sedimentation. If all the particle will be same size, then there will be same rate of sedimentation. But this thing is practically not possible, because if all the particles will be the same size, then it will be a monodispersed particle. So, why you are going to determine the rate of sedimentation and equivalent diameter? There is no need to determine all these things. This is the exact thing. अगर सब चीज़ spherical है, सब कुछ uniform है, monodisperse है, तो उस केस में हमें ये आगे एवरेज और इक्विवेलेंट डायमीटर, एवरेज पार्टिकल साइज डिटरमाइन करने की रिक्वायरमेंट नहीं, क्योंकि जो एग्जैक्ट पार्टिकल साइज होगा वही एवरेज होगा, बिकॉज ऑल द पार्टिकल्स आर द मोनोडिस्पर्स इन नेचर, ऑल द पार्टिकल्स हैव द सेम साइज. बट प्रैक्टिकली ऐसा नहीं होता, पार्टिकल्स में एसिमेट्री होती है और दे आर पॉलीडिस्पर्स इन नेचर. दैट्स वाई वी आर स्टडिंग दिस एवरेज पार्टिकल साइज डिटर्मिनेशन, सरफेस एरिया, फ्लो प्रॉपर्टी, ऑल दीज थिंग. सो एज यू सी इन दिस पिक्चर, सारे पार्टिकल में एक साइज़ के नहीं बनाए कि सारे ऐसे ऐसे ऐसे, कुछ पार्टिकल बड़े हैं, देन स्मॉल, देन स्मॉलेस्ट, बिकॉज दिस इज द पॉलीडिस्पर्स. यही तो पॉलीडिस्पर्स पाउडर पार्टिकल साइज डिस्ट्रीब्यूशन है. अगर सारे सेम होते तो मोनोडिस्पर्स होता. सो एज यू सी इन दिस पिक्चर, दिस इज द पॉलीडिस्पर्स इन नेचर, यानी कि जो कैल्शियम कार्बोनेट के पार्टिकल आपने वाटर में सस्पेंड किए हैं, दिस कैल्शियम कार्बोनेट पार्टिकल्स आर द पॉलीडिस्पर्स इन नेचर. कुछ बड़े हैं, फिर उससे छोटे हैं, फिर उससे छोटे हैं. अब ऐसे सी द रेट ऑफ सेडिमेंटेशन, जो बिगर पार्टिकल है उनका रेट ऑफ सेडिमेंटेशन फास्ट है, बिकॉज द रेट ऑफ सेडिमेंटेशन दैट मीन्स द ग्रेविटेशनल फोर्स, एंड ग्रेविटेशनल फोर्स इज प्रोपोर्शनल टू द मास ऑफ द बॉडी, एंड इफ द मास ऑफ द बॉडी विल बी मोर, then the rate of sedimentation will of course move. So, in case here as you see in the picture, the bigger particle have more rate of sedimentation. See, यहाँ जो बड़े बड़े पार्टिकल थे वो जल्दी जल्दी नीचे सेटल होने लगे. दिस इज द ब्लैंक, ओनली द लिक्विड. एंड इससे जो थोड़े बड़े पार्टिकल्स थे वो यस पोजीशन पे है, और जो सबसे छोटे पार्टिकल्स थे वो वहाँ. तो by visualizing, by keep watching this by seeing this picture, you can analyze or say the rate of sedimentation of bigger particle will be more, क्योंकि जो ये पार्टिकल है ये बहुत जल्दी 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 सेटल होंगे, और जो छोटे छोटे पार्टिकल होंगे वो काफ़ी लंबे टाइम तक उस सस्पेंशन में या उस डिस्पर्सल में सस्पेंडेड फॉर्म में रहेंगे. तो आपको हर 10 मिनट्स में आई हैव टू विड्रॉ, एंड आफ्टर ईच 10 मिनट टाइम इंटरवल यू हैव टू विड्रॉ द 10 ml liquid in a pre-wetted china dish. So just evaporate that liquid and weigh out that the solid particle which we have suspended, and then tabulate the data as in the previous method, since sieving and optical microscopy method. First column belong to serial number, second means the time is 10 minutes. So initially 10 minutes, then again 10 minutes, 10 plus 10 20, then 30, then 40, then 50, then 60, but the time interval is fixed, that is the 10 minutes. We should keep the fixed time interval throughout the experiment. Next one is the height in centimeter. And what is the height here? See, in this Anderson pipette, suppose that initially this level is up to this mark. When we withdraw a 10 ml sample in this sampling bin, the level will be like this. Again withdraw the 10 ml, then water level will this dispersion level will reach just up to this. Then again withdraw 10 ml. In every subsequent withdrawal of the 10 ml, there is a fluctuation or there is a change in the sample height. This is the height of the sample which liquid which you have filled in this. So you have to measure this change in this height. So this is the height. This is the fixed time interval. Here you have to determine the Stokes diameter. For the determination of particle size by sieving method and optical microscopy method, there was the same formula, that is the sigma nd upon sigma n. But for the determination of powder particle size by sedimentation method, there is a different formula, because here we are going to determine, or we are determining the Stokes diameter, and for the Stokes diameter we are using the Stokes law. And for the Stokes law, how will you calculate the diameter? This is the Stokes formula, dSt. See, d is the diameter, st for the Stokes. So by if you anywhere it is written dSt. So by seeing this dSt, we can identify, yeah, this is the equivalent diameter, and which type of equivalent diameter, what parameter we have considered, that is the Stokes diameter, that is the rate of sedimentation. And if there is d sieve, then we automatically we know, okay, d sieve, that we have determined this particle size by sieving method. If it's a dp, okay, हाँ इक्विवेलेंट डायमीटर तो है क्योंकि एसिमेट्रिक पार्टिकल है, लेकिन इक्विवेलेंट डायमीटर डिटरमाइन करने के लिए हमने कॉन्स्टेंट पैरामीटर क्या लिया, किस चीज़ को हमने स्फेरिकल पार्टिकल से कंपेयर किया, किस पैरामीटर को स्फेरिकल पार्टिकल से कंपेयर किया, दैट इज प्रोजेक्टेड एरिया. So here the dSt, Stokes diameter, the formula for the calculation of Stokes diameter is 18 eta v upon rho s minus rho 1 z to the power 1 by 2. So here dSt the Stokes diameter which you have to determine. Eta is the fluid viscosity. Here if I have prepared calcium carbonate suspension in water. So fluid viscosity, that means the viscosity of water. Density of the solid, कौन से पार्टिकल लिए हैं, कैल्शियम कार्बोनेट, तो डेंसिटी ऑफ द कैल्शियम कार्बोनेट. रो 1 डेंसिटी ऑफ द लिक्विड, किसकी डेंसिटी, वाटर की डेंसिटी. सेटलिंग वेलोसिटी, दिस वेलोसिटी यू हैव टू डिटरमाइन. G, acceleration due to gravity, that is 9.8, this is fixed value. So in this formula what is unknown, this is V. सेटलिंग वेलोसिटी, यानी कि किस रेट से पार्टिकल इनिशियली कहाँ है, ऊपर रहेंगे, तो किस रेट से पार्टिकल धीरे 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 नीचे बॉटम पे आके सेटल हो रहा है. ये एक पार्टिकल है धीरे 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 किस तरह नीचे आके सेटल हो रहा है, जो सेटलिंग वेलोसिटी है, दिस इज द वी हैव टू डिटरमाइन V, एंड बाय आफ्टर डिटरमाइनिंग दिस सेटलिंग वेलोसिटी वी हैव टू कीप द डेटा हियर and then determine the dSt. And how will you determine this settling velocity or rate of sedimentation? The formula for determination of the settling velocity is V equal to h upon t. H is the height and t is the time. This is the height and this is the time. कहाँ से आपको टाइम और हाइट मिले? टाइम तो आपने फिक्स इंटरवल किया था 10 मिनट. हाइट क्या थी? जब आप हर बार 10 ml 10 ml 10 ml विड्रॉ कर रहे थे तो कितना लेवल उसमें रह रहा था, कितना लेवल फ्लक्चुएट हो रहा था, वो लेवल आपने यहाँ पे लिखा है. तो एंडरसन पिपेट से आपको टाइम्स जो फिक्स्ड टाइम इंटरवल आइदर 10 और 20 मिनट, और ये हाइट आपको एंडरसन पिपेट से मिल गई. इससे आपने v निकाल लिया. इस v को आपने इस फॉर्मूले में रखा, आपको dsT मिल गया. इन वैल्यूज़ को अगर आप इस पे रखोगे then you will get the 1 2 3 4 5 6 stroke diameter you will get, because you have taken in here the 6 time you have withdrawn the sample. Now you have to add on all the 6, this you have to add on this 6 stroke diameter divided by 6, then you will get the average DST. Okay, in this way you can get the average stroke diameter. आपने इसका स्ट्रोक डायमीटर अलग निकाला, इसका अलग निकाला, इसका अलग निकाला, क्योंकि हर बार there is change in a Vn. So T is almost constant, is 10, but every time height is changing. So by keeping this h and t, we can determine the stroke diameter 10 minutes, after 20 minutes, after 30 minutes, 40 minutes, 50 minutes, 60 minutes, और जो ये diameter आएगा उन सबको ऐड करना है. This is number 6, so we have to divide it by 6, then will get the average stroke diameter by sedimentation method using Anderson pipette. Now this is all about the particle size analysis, but where you have to determine the particle size distribution also. So for the determination of the particle size distribution, in x axis always the particle size, in y axis always the frequency. और जब भी weight distribution की बात होती है तो वो frequency weight retained पे जो चीज़ weight retained होता है जो powder, that is known as the frequency. जब बात माइक्रोस्कोपी की होती है तो जो हम वो पार्टिकल्स मेजर करते हैं, जो काउंट करते हैं, दैट इज़ नोन एज द फ्रीक्वेंसी. सो ये वेट डिस्ट्रीब्यूशन है, तो यहाँ फ्रीक्वेंसी क्या होगी? जैसे वेट, कौन सा वेट? जो हर 10 मिनट्स में आप विड्रॉ कर रहे थे प्री वेटेड चाइना डिश में और उसे एवोपरेट करने के बाद लिक्विड जो आपको सॉलिड पार्टिकल्स मिले थे उनका वेट. दैट वेट यू हैव टू keep out that weight which you have obtained after 10, 20, 30, 40, 50, 60 minutes, you have to put this data here. Now percentage weight retained, how will you determine this? Suppose that it is x and its total is z, then how will you determine this percentage weight retained? X divided by z multiplied by 100. Okay. Percentage cumulative weight retained, same formula for the percentage cumulative weight retained. For example, 1, 2, 3, 4. In the first column it will be 1, in the second diagonal add up 2 plus 1, 3, next for diagonal 3, 3, 6, again diagonal 6 plus 4, 10. So in this way you can determine the cumulative weight retained. So by stroke diameter formula you can determine the average particle size by average stroke diameter, and by plotting the frequency distribution curve you get the average particle size distribution. For the frequency distribution curve, in a x axis always this, in a y axis one time you keep this, this and this, you will get the 3 frequency distribution curve. यानी कि पहली frequency distribution curve में x axis पे stroke diameter, y axis weight of solid. Second frequency distribution curve, x axis stroke diameter, y axis percentage weight retained. Third frequency distribution curve, x axis strokes diameter, y axis percentage cumulative percentage weight रिटेन. सो जो ये वेट रिटेन, परसेंटेज कुमुलेटिव वेट रिटेन के जो ये कैलकुलेट करते हैं, दिस वी आर कैलकुलेटिंग टू ड्रॉ द फ्रीक्वेंसी डिस्ट्रीब्यूशन कर्व, और दिस इज फॉर द कैलकुलेशन ऑफ द एवरेज पार्टिकल साइज. So in this way we can tabulate the data and calculate the average particle size or a stroke diameter of the powder particle as well as the particle size distribution by Anderson method or a sedimentation method. This is the formula for the calculation of the stroke diameter. Advantages and disadvantages of a stroke diameter, or the this is not for the stroke diameter, this is advantages and disadvantages for this method, the sedimentation method or Anderson pipette method. Now, next method. With three methods we have studied. One is the sieving method, second one is the microscopy method, this is third one was the sedimentation method. Now, fourth method is known as the Coulter counter or conductivity method. Basically, this is not exact, it's a direct method to determine the particle size or particle diameter. By this method, so by Coulter counter method or conductivity method, you can determine the particle volume. If you know the particle volume, you can easily obtain the you can calculate the diameter, because you know the this volume of the sphere. What is the volume of the sphere? 4 by 3 pi r cube. So, if you get the value of volume by putting this volume value of this particle, the pi is the fixed value. So, you can in this way you can calculate the r, and if you multiply r with 2, then you will get the diameter, and diameter is the particle size. So, Coulter counter और conductivity method से हमें क्या मिलता है? पार्टिकल का वॉल्यूम, जिससे हम we can determine the particle diameter also. So, basically three direct methods for determination of particle size, that is the sieving, sedimentation and microscopy method, and one fourth method is used for the volume determination. By volume determination, in this method we can also determine the particle size. So, the Coulter counter is the name of the scientist who invented this Coulter counter experiment, and this is also known as the conductivity method. As you know the conductivity method, that means for this method the solvent, the vehicle which is used for the dispersion or for the preparation of the suspension should be a good conductor of the electricity. So, Coulter counter, they are two brothers. They were and these people have invented that Coulter counter to analyze, basically to analyze for the analysis of red blood cells or red blood counting. So, after that when that's atomic bomb blast during second world war in Hiroshima and Nagasaki. So, if whenever there is any such type of casualty, so there are two types of effect. One is the instant effect, either people will survive or die. And the second one, whosoever is survived in this during this war or this nuclear blast, they may develop some genetic disorders. They can be hereditary for the next generations also. They may born with a congenital disorders. So, जो लॉन्ग टर्म इफेक्ट आते हैं उन लॉन्ग टर्म को एनालाइज, उन इफेक्ट को एनालाइज करने के लिए देयर इज वन वे इज द रेड ब्लड सेल्स एनालिसिस. तो आफ्टर दिस वर्ल्ड वार क्या देयर इज अ नंबर ऑफ पेशेंट्स आर कमिंग फ्रॉम फॉर द एनालिसिस ऑफ देयर रेड ब्लड cells, or because these are the way to detect the subsequent or carcinoma or cancer or some other type of diseases which might be occur in the places where this type of that type of explosion was there. So, that is why what was the traditional method to determine the RBC? Just simple optical microscope type method. We make a smear, put the smear of that blood in that slide, and this monitor each and every slide through with the help of this microscope by using this ocular or whatever this eyepiece. So, that was the tedious method. तो उस method को replace करने के लिए, उस method से fast करने के लिए method, the Coulter and counter have this Coulter counter. These people they had invented apparatus that is known as the Coulter counter or conductivity method. So, basically that instrument was invented for the analysis of RBC, and since this method can't recognize the cell is living or non-living, so that's why this is also you can also use this for the determination of the powder particle size analysis. So, the first automated blood cell counter came out in the 1950s based on the Coulter electrical impedance principle. The Coulter counter states, or Coulter principle states that if a suspension of a blood cells is passed through a small restriction simultaneously with an electric current, the cells will modulate the current, so enabling them to counted and sized. which gained worldwide renown as the Coulter counter. So, initially it was the first automated, the name was the automated blood cell counter, which was later on it will gain later on it was gained the worldwide name as a Coulter counter. So, it will determine the particle size in range of a 0.5 to 500 micrometer. This is the assembly of Coulter counter. In this apparatus, see, this is the mercury manometer. What is the use of mercury manometer? Pressure. So, generate the pressure. Mercury manometer is for the pressure measurement. And this is the sample cell, and the sample cell is again connected to the circuit, and this amplifier, threshold current, pulse amplifier, counter drive, digital register, and this is a counter switch. So, whenever you switch on this counter switch, this process will start to begin. Okay. So, what will happen? How will you determine the particle volume by this Coulter counter method? So, there are different steps for this determination. First one, what is the working principle of this Coulter counter? For the determination of the powder particle size or particle volume by this Coulter counter method, first particles are suspended in a conducting electrolytes. Conducting electrolyte मतलब ऐसा vehicle जो इलेक्ट्रिसिटी का गुड कंडक्टर हो, जिसके थ्रू इलेक्ट्रिसिटी पास हो जाए. अगर आपने कोई सस्पेंशन कोई मतलब ऑयल में बना दिया तो ऑयल इज नॉट गुड कंडक्टर ऑफ इलेक्ट्रिसिटी. सो इन दैट केस दिस मैथड वी कैन डिटरमाइन बाय यूजिंग द Coulter counter. So for the Coulter counter method, the vehicles should be a good conductor of electricity. For example, here again I am going to determine the calcium carbonate particles volume. So, first I have to disperse this calcium carbonate particles into a NaCl solution in water. Why? NaCl में Na plus Cl negative. This is anion and cation, good conductor of electricity. So, I have a vehicle. What is the vehicle? NaCl dispersion in NaCl solution in water, and in NaCl solution we pour that mix that calcium carbonate particles. Now, I fill this calcium carbonate suspension in the Coulter counter apparatus to determine the particle volume. So, particles are suspended in a conducting electrolyte, for example, NaCl solution in water. This dispersion is filled in a sample cell that has an orifice and maintains contact with the external medium, which will also be a NaCl solution in a water. So, electrode are placed in the suspension inside the cell as well as in the electrolytic solution, that is outside the cell. When the suspended particles travel through the orifice, it displaces its own volume of electrolyte into the beaker. Then the net result is a change in electrical resistance is called voltage pulse, and this voltage pulse is proportional to the size of the particles versus the volume of the particles. So, number of pulse is equal to the number of cells counted, and the pulse height is directly proportional to the cell volume. This system, the assembly of this Coulter counter we can divide in two parts. One is the electrical system and output system. One is the electrical system device and second one is the output system. Electrical system जहाँ पर आप सैंपल भर रहे हो, इलेक्ट्रोड लगा रहे हो, और आउटपुट डिवाइस जहाँ से आप उसके आउटपुट सिग्नल मिल रहे हैं किसी सिग्नल के फॉर्म में, और उस सिग्नल को आप डिकोड कर रहे हो ना डिजिटल वैल्यू. So, जो भी pulse मिलेंगे, that pulse produced at the orifice are amplified and displayed on the oscilloscope screen and appears as a vertical lines or as spikes. So, oscilloscope similar to just like a ECG. जो electrocardiogram होता है, ECG you get the pulse like this. So, these are not a digital. These spikes should be converted into the digital, decoded into the digital form. Then you can obtain that the volume of that particle. And by getting the volume of the particle, as we know the sphere particles have the, so the volume of a sphere is V equal to 4 by 3 pi r cube. So, we get the volume directly, and you can also determine the particle size by getting this volume. तो फर्स्ट वन इज़ द इलेक्ट्रिकल सिस्टम, जिसपे कि आपने सैंपल को फिल किया और इलेक्ट्रोड लगाए, मैनोमीटर फिक्स किया, जिससे कि उसमें इम्पीडेंस आया, फ्लक्चुएशन हुआ, जो कि वोल्टेज फॉर्म में वहाँ पे रिकॉर्ड हुआ। अब जो वोल्टेज फॉर्म में जो ईसीजी की मशीन की तरह जो आपकी पल्स आई, उन पल्स को एनालॉग सिग्नल, दिस आर नोन एज द एनालॉग सिग्नल. So now next step is to convert this analog signal to the digital signal, so that we can easily read out this data. So next step or next attachment in this Coulter counter is the analog to digital converter, where we can convert this analog ECG type of analog pulses into the digital form. So analog wave is sampled at some interval and then turn into a number that are stored in the digital device, and we can easily visualize or easily understand this the digital numbers or digital value in the form of the this particle volume. So there are some disadvantages and advantages of this Coulter counter. So now again come to this image, this picture of this Coulter counter. So what we have discussed now, what we have just studied right now. So this is the Coulter counter, this is the arrangement of Coulter counter. As we have studied right now, there are two type of arrangement. This is the output, as we studied here, na? One is the electronic system and second one is the output system. This is the electronic system. अब कैसे ये Coulter काउंटर काम करेगा? इस सिस्टम का कुछ काम नहीं है, इस आउटपुट सिस्टम का काम क्या है? जस्ट टू कन्वर्ट द एनालॉग सिग्नल इनटू द डिजिटल फॉर्म, सो वी कैन इजीली रीड आउट, इजीली डिकोड द डेटा. So this is the whole assembly of Coulter counter. This is the mercury manometer and this is the sample cell. This pink was the sample cell, in which this is sample cell having a calcium carbonate सस्पेंशन, और ये सस्पेंशन किस में बना हुआ है? NaCl में, विच इज़ गुड कंडक्टर ऑफ इलेक्ट्रिसिटी. और दिस बीकर, इसमें भी NaCl सॉल्यूशन है. Now what will happen when you switch on this counter switch? There is a mercury manometer, so it will create a pressure. When it will create the pressure, there is no opening here. There is only opening in this sample cell. This is the orifice, this orifice. So what will happen? If you are creating a much more force from this side, and this is the liquid is filled here, and there is only one opening, this is this. So what will happen? कहीं से भी पार्टिकल्स को बाहर निकलने की जगह नहीं मिलेगी. इधर से बहुत ज़्यादा फोर्स लग रहा है, कहाँ जाएंगे वो? जहाँ भी उन्हें ओपनिंग नहीं मिलेगी वहाँ से वो बाहर आएंगे. सो व्हेन वी क्रिएट द प्रेशर फ्रॉम दिस, द पार्टिकल विल ट्रैवल एंड वेयर दे विल गेट द पाथ टू कम आउटसाइड थ्रू दिस ऑरिफिस. इस ऑरिफिस से वो बाहर आएंगे. जब वो बाहर आएंगे तो बाहर किस में आएंगे? दे विल कम इन दिस सॉल्यूशन. What is this solution? This is the same electrolytic solution which you have filled in the sample cell, with here this electrolytic solution along with the suspended particles of calcium carbonate, but here only and only the pure electrolytic solution. और जितना भी वॉल्यूम इस पार्टिकल का होगा, सेम वॉल्यूम इस लिक्विड में फ्लक्चुएट करेगा वो. सिमिलरली इफ यू हैव अ bucket filled of water, then what will happen if you pour, or we just flash one stone on that water? What will happen? Whatever the volume of that stone, that much amount of water will spill out from that bucket. This is the bucket, or this is a beaker full of the water, and we put our stone on this. What will happen? Whatever the volume of this stone, that stone will spill out the water from this bucket or from this container. So similarly here, whatever the volume of that particle which will expel out from that orifice to this NaCl solution or the electrolytic solution, it will fluctuate, it will displace this liquid variable. कितना डिस्प्लेस करेगा, उतना ही जितना इसका वॉल्यूम होगा, और वो डिस्प्लेसमेंट इट विल क्रिएट, देयर इज अ एनोड एंड कैथोड आल्सो इंसर्टेड हियर, सो दैट विल क्रिएट एन फ्लक्चुएशन इन दिस करंट, and this current fluctuation, this impedance is recorded in here, this scope that is known as the oscilloscope, that is recorded in this oscilloscope in the form of the pulse height, and this pulse height is directly proportional to the particle volume, and this is in the form of the analog signal. This will be converted into the digital signal, and in the digital signal we can also determine the particle volume. So, this is the whole assembly of the Coulter counter. But mandatory requirement for the Coulter counter is this: the vehicle which is used for the dispersion, to prepare the dispersion of the particle, should be a good conductor of electricity. So, this is the whole assembly of Coulter counter. So, in this way we can determine the powder particle size. So, here in this lecture we have studied two methods for the determination of powder particle size. One is the sedimentation method and second one is the Coulter counter method. Coulter counter method is basically used for the particle volume determination, and sedimentation method by using Anderson pipette for the determination of the powder particle size by the weight distribution methods. So, this is all about for the today's lectures. Thank you.